Hi, and welcome to VEX in Houdini. I'm your instructor, Sean Lepowski. And before we get started, I've got 7 brief slides, just giving you a broad overview of the language. Hopefully this is not your first programming language. As I said in the class requirements, I recommend you know at least one other language. Hopefully something C-like as well, because VEX is very C-like. But if you're comfortable in Mel, if you're comfortable in Python and any of the other visual effects scripting languages, you're probably going to do okay in this class. So let's get started. All right, first question. What is VEX? It is not a general programming language. You're not going to be writing desktop applications. You're limited to writing small VEX programs within Houdini or within OTLs, which are digital assets that can be ported to Maya, Max, anything else that supports the Houdini engine. One big limitation with VEX is you're constrained by the I/O functions. So if you're reading or writing to disk, you're going to have to stick with what side effects provides you, which is great for point clouds, volumes, all the visual effects file formats are there. You can read them incredibly quickly and write, and it's incredibly efficient at dealing with those things. But if you wanted to write a custom I/O function, you're not going to be able to do that. You don't have the sort of low-level access you would have in C to do things like that. VEX, when I say it's from a shading pedigree, I'm referencing the fact that it's inspired by RSL, RenderMan shading language, and all of Houdini's shaders are written in VEX. That was its strong suit from the beginning, but now it's sort of branched out to include modification of geometry, and in the latest version of Houdini, even creation of raw points and edges and polygons. VEX is parallel, so if you have millions and millions of points and you have 16 threads, it will automatically break up those points into 16 chunks and process them simultaneously. You don't have to think about that. It will handle it for you. It will have some effect on how we write our routines, as we see later, but for the most part it's pretty painless compared to what that would be like if you were handling it yourself in your own plugin for Houdini. VEX also has a visual component, which is VOPs, so it's a great way to get people programming without even realizing they're programming. They'll just be connecting nodes like it's another Houdini context, and if you just right click on your VOPs network, you'll see that it's actually compiling that. It's actually creating code that is then converted from its VFL state to its VEX state. VFL is when it's text. .vex files are an intermediate format that is, not really very human readable anymore, but it's at that stage it becomes optimized. And last but not least, VEX is incredibly context dependent. And within Houdini you have your normal SOPs, ROPs, CHOPs, all these different contexts for doing different things. Those can be subdivided further into the individual VEX contexts. So let's look at an example of that. So if we're dealing with geometry, the SOP VEX context has certain global variables that are available to you. P is for position, N is for normal, PTNum is the number of the current point you're working with. In PT, that capital N, lowercase pt, is the number of points coming into the VEX node that you're creating. CD is color, so you get a lot of freebies. And those change in every context until you get to the lowest level VEX context, CVEX, which we'll also be dealing with pretty soon. This is the only context where you can create geometry. And as such, being low level, it doesn't give you anything for free. So we're going to have to do a little bit more work there, but it's incredibly powerful and incredibly freeing. So VEX has some basic types. Float, int, and string are just like you've used in other languages before. You are limited in terms of your precision. You don't have the near infinite precision you get with Python, and you don't even have double types, but it shouldn't affect anything we're doing in this class. Any of the algorithms we're implementing will be fine to implement as 32-bit algorithms. Unlike a lot of other languages, it includes vector and matrix types, the linear algebra types. So vectors are for storing points or colors because you have 3 or 4 components, X, Y, Z, RGB. And matrices are for transforming points or colors even. And these types, if you have a bunch of floats, you can store them in an array. That's one way you can extend your basics. Or you can create structures now in the latest version of Houdini, which is a nice new feature. It's not as sophisticated as the sort of structures you might create in an object-oriented language where you can, you don't just encapsulate data, but you'd encapsulate functions as well. And last but not least, the mysterious bidirectional scattering distribution function type. We will not be defining our own BSDFs, although we may be blending the predefined BSDFs together. So a BSDF is just a way of describing how light interacts with a surface. So you might have seen the bidirectional reflectance distribution function, BRDF is that acronym, or BTDF, which is the transmittance function. Those are functions that describe, of course, how light reflects off of a surface and how light is transmitted through a surface. Well, the BSDF, encapsulates both of them. It's the complete function for physically based rendering. That could be a class of its own. That's why we won't be covering it in detail in this class. Maybe down the line I will get to cover it, or another instructor. And finally, the last thing to know about variables in VEX is that because there are no pointers, you're not going to overwrite random places in memory and bring Houdini in your operating system to a crashing halt, which is great. All right, VEX control structures. So you've got your basic branching, if, else, right? That looks like any other C-based language. When you're looping over stuff, you have the while, which is, again, like any other C-based language. You've also got a form of that where it's, do something in this block of code first, no matter what, and then it will run the condition to test whether it keeps looping over it. You've got the standard for and for each. Syntactically it might be different than what you're used to, but it's, again, very similar to Mel, C++. Alright, so VEX functions are basically C functions. They're even simpler. Foo is the function name, int is the value, the type of the return value, and in parentheses here we have our 3 arguments, A, B, and C. And if you've got consecutive arguments of the same type, you can shorthand it and just use a comma to separate them. Otherwise, always use a semicolon to separate the parameters you pass into the function. And of course, the logic of the function, the body, exists between curly brackets. Absolutely C++-like. One thing to note is that VEX has function overloading. So here I've got a contrived example. There is no real square me function. You just call the power function. But I've defined square me twice here. The first one takes an integer, squares it, and returns an integer. The second one takes a float value, squares it, and returns a float. And VEX will basically call the one that makes sense. So if we had a float value that we passed in as an argument to the function, it would return a float automatically. Whenever there's ambiguity, you need to give the compiler a hint. So there is such a thing as function casting, and we will cover that at a later date, but I would like to show you in the documentation right now what function overloading looks like. This is the clamp function. You'll use this a lot. Clamp, fit, a lot of other basic functions that are common to any sort of expression language in visual effects software. In clamp, just it takes a input value and fits it between the min and the max, and it's been defined for 4 types of values. So nothing weird there. And the final thing to note about VEX functions is that there's no recursion. And I say usually there because the one sneaky exception is with shaders, because shaders can call themselves. That means that when you write a shader in VEX, you can call it again as a shader, which could then further call it again as another shader call. So you can hack recursion into the system, but we won't be using it at all in our examples. Alright, and last but not least, we have the VEX preprocessor. So this is like C macros. The preprocessor is a pass that is run over your code before it's actually compiled into an actual executable node. So include is just going to bring in an external VEX file. So if you've written a bunch of functions somewhere else, you can bring them into the current program. You can define constants for efficiency. Like here, I've defined pi as an example because pi never changes. So it makes it very clear to stick that define at the top of your program as opposed to stuffing it into a variable, because that value does not need to vary. And you've also got pragmas. You guys are going to grow to hate these. Pragmas are special instructions for defining interfaces. So when we add sliders, float sliders, and graphs, it's going to be through pragmas. Alright, that's it. You guys made it through that boring ass slideshow. It's 10 minutes of torture, I know. But to get you excited about the next part, I will give you a little sneak peek. The first thing we're going to do is implement a couple of VEX deformers. One is going to flatten our dragon. The other is going to puff this dude out. And we're going to look at how to do that in a couple of different ways, using VOPSOPs, wrangle nodes, and actually creating a digital asset and doing it the traditional way. And then once we're comfortable with VEX and its various incantations, we're going to attempt the 2D version of the super formula, and we're going to be pushing points around with super formula, and this is the resulting render. And as part of your homework, you guys are going to be extending super formula into the third dimension. It'll also serve as a great introduction to polar coordinates and alternate coordinate systems. And then after that, we'll finish up with an example of phyllotaxis, which is the really cool spiral-like organic arrangement you see in nature and plants and a lot of other things that is related to the golden ratio. So we'll be talking about golden numbers, golden angles, and again, we're going to be working in polar coordinates, so it'll serve as a great exercise as well to introduce those. So let's get started.